In the last section, we went through when we figured out how to go from the periodic table, and we already knew how to get electron configurations, and we figured out from there how to get into the shorthand notation. Okay, you went through that process. If not, go back and watch that video. It's there for you. But I'm going to show you something. Right now, we can go through, and if we have the element, we can kind of figure out the electron configuration. We always have this chart. Then we can go back and do a comparison. We're starting to learn where we can do this. But we can also use the configurations to go backwards to figure out the element. So with this, go through, and I'm going to ignore this first one because I didn't teach you guys the D's. But let's go to this next one. I want to know what element it is. There's two ways you can do it. I can sit there and count these up because these represent the electrons. Those are all of these things as you put them in. Okay. Now that's going to be a long process and it's easy to miscount, stuff like that. A quicker way is this. I look at the very last piece. Okay. This is my period. This tells me my group. So I'm going to go 5. There's my period. Everything here is an S2. So 5S2 is strontium, SR. So you can use these both ways. 3P5. Well, 3 P5's here. So 3P5 is going to be chlorine. Next one. That definitely looks intimidating. And trying to count up those electrons and keep them straight, definitely you could do it, but just question yourself. Okay, but I'm just going to go this route. 6P3. There's 6. P's up here. There's 3. 6P3 is this, bismuth. Okay. So there we go. Hopefully that made a little bit more sense. Now let's go ahead and go through and figure out the shorthand form, just as a quick review. If I'm right here, I'm looking for strontium, my last noble gas. Up one all the way to the end, it's Kr. And Kr ends in a 4P6. So anything 4P6 or below is taken care of just by writing Kr. Sorry, that's a really bad K. So now I just write whatever's left. And you can do the same thing for chlorine. Its last thing is neon. Neon's going to be a 2P6. So there's 2P6. Neon, and then I write whatever's left. So just doing a quick review. On bismuth, right here, last one is xenon. Xenon ends in a 5P6. So 5P6 and below. I'm going to put Xe. And then I write whatever's left. Don't worry about the F's and the D's. We'll get to that later if we have time. The D's definitely we'll get into. F's not so much. Okay, so this would be the shorthand for that. Okay. So hopefully that makes sense. Now, we're going to go from there knowing these and being able to come up with the shorthand notations. Okay, very things. We're going to go to what's called the next thing, which is called Lewis dots. Lewis dots help us because it shows the electrons that are involved in chemical reactions. It shows the outermost ones. Once again, those are the valence electrons. Those are the ones that make everything happen. So we've already started setting the stage for the valence electrons and for Lewis dots. Now, there's a lot of different ways you can do Lewis dots. I do it this way. This is the way I was taught. I ask you guys to do the same thing because it's an easy way for us to always compare, be able to check answers against each other and talk. It's a standard format, standard language. There's a lot of different ways you can do it, though. You're going to see it probably different ways depending on where you look for a website. Lewis dots, they show only the outermost electrons. These are the reactive ones. These are the ones we care about. We call them valence. 8 electrons is the maximum. Remember when we go over, it was the S's and P's. S is 2, P's are 6. So if we count it across, 1, 2, 3, 4, 5, 6, 7, 8, and then we restart. So Lewis dots, we're only going to go up to 8 total. 8. Keep that in mind. Now there's the set format that I will always be using, and I'm going to encourage you guys to as well, is this. So we're going to do this, and if you think about it, there's 4 sides to this symbol. Okay. I'm going to treat each one of those as basically kind of an orbital, one of these. But I'm going to start and do it slightly different. If I'm tracking the S's, I'm going to put both S's, or however many S's they have, on this side. Each side can only hold 2 electrons, just like each one of these orbitals could only hold 2 electrons. I'm going to put S1 and S2 on this side. You don't have to have them like top and bottom, just somewhere on that side. Okay. When I go to do the P's, though, remember P's can have a total of 6. I spread them out, and you'll see later why spreading out will be helpful. On the bottom somewhere, I'm going to have P1. P2 is going to go here. And then P3 is going to go on the top somewhere. Now, why did I spread it out like that? Well, if you go back, remember Hund's rule. Hund's rule said when we're adding electrons, we're always going to spread them out, one in each orbital, before we double up. Remember, electrons are negative charge. They want to get away from each other. So they're going to spread out. So that's what I showed here. These are those 3 orbitals, those 3 lines. Now I go back and I double up. P4, P5, P6. Okay. So there is my full 8, my full octet. If anything goes all the way up to P6, it's a noble gas, okay, with the exception of the free. But all the rest are going to be noble gases if they have that. So hopefully that piece makes sense. That's pretty straightforward. Shouldn't be that much of an issue for you. But here's where it's going to come together. This is what we've been building to. Okay. If we were to look at hydrogen, I'm going to show you right now how to do Lewis dots. If I were to look at hydrogen, I can look on the periodic table, or I can go back to doing this, or I can look at one phone. I'm juggling so many papers. I can look at this. I can look at longhand, or I can look at shorthand. It doesn't matter. But I'm going to look at the very last stuff that's listed beyond the noble gas. For hydrogen, there's 1 electron. Just use this. So for hydrogen, if I'm going to do a Lewis dot, Lewis dots only show the outermost electrons. And hydrogen has 1 electron, and it's an S1. So I'm just going to say over here, I'm going to put a single dot, hence Lewis dot. That shows me hydrogen has that many reactive electrons. If I'm going to go to helium, no Lewis dot or no noble gas fire. So before, what we have here is our reactive electrons. It's got 2. Remember I said with the pattern I use that it's going to be the S's are going to go on one side. And yeah, I lost that piece of paper. There we go. S's are going to go on one side. So I'm just going to go and do that. If we continue on, once again, you can do it off the periodic table. You can do shorthand, longhand, doesn't matter. Look at lithium. And I want the thing at the very end, the highest energy level, and then how many electrons are there. So this has 1 electron. So if I go do Lewis dot for lithium, there's my 1s. There's the 1s that it showed. Beryllium. Beryllium is a 2s, or an S2, sorry. So there's S1, there's S2. Boron, covering this up, There's S2 and there's P1. Following our pattern, the S is on the side, P1 goes on the bottom. So S1, S2, P1. Now, I didn't go through on this and cover boron, carbon, and oxygen, and all that stuff. But then again, I really don't need to, because basically I'm moving across this periodic table. Let's face it, you've marked that boron is P1. Carbon is going to be a P2. So with that, S1, S2, carbon, there's my P1 goes on the bottom, and then my P2 goes somewhere on that side. Doesn't have to be top, it could be center, as long as it's on the correct side. Nitrogen, next one over. I'm adding another electron. Well, that's going to be our P3. S1, S2, P1, P2, P3. It has 5 valence electrons. Now check it out. 1, 2, 3, 4, 5. There's its 5 valence electrons. Those are the reactive electrons. Oxygen's one more over. S1, S2, P1, P2, P3, P4. There's my 6 valence electrons. 5, 6. Fluorine, S1, S2, 1, P1, P2, P3, P4, P5. Because that ends in a P5. There we go. And then go on to neon. Neon's a noble gas, so it automatically has to have 8 dots total, 2 on every side. S1, S2, P1, P2, P3, P4, P5, P6. There's my 8 electrons. There's my full octet. Now, if that makes sense, everything else now is a piece of cake. Because if we look, hydrogen was 1 dot, ends in an S1. Lithium, 1 dot, ends in an S1. Sodium ends in an S1, so it's going to be 1 dot. K, which is right below that, right here, is going to end in an S1, 1 dot. Beryllium ends in 2 dots. It's an S2. Well, that means magnesium, which is right below it, is going to have 2 dots. Calcium, right below that, is going to have 2 dots. Aluminum, right underneath boron. Boron had 3 dots. So aluminum is going to have 3. Gallium, right below that, is going to have 3. We're seeing patterns that are set up. The valence electrons are all matching within a group. And that gives us very specific properties to things. Silicon is right under carbon. Phosphorus is right under nitrogen. So we have basically a repeating pattern, okay, a repetition of properties as we go through. And that's the same all the way through the periodic table. Everything in this group right here is always going to have 4 valence electrons. The 2 S's and then the 2 P's. Okay, it doesn't matter which one of these it is. It's always going to have that number of valence electrons. So hopefully that makes sense on how to get the Lewis dots as to how it's generated off this. We keep seeing more and more shortcuts because ultimately we went from longhand configuration, electron configurations, from these down to these, fine-tuning on the electrons. Now we're going to be moving into this and going to additional stuff built off that. So hopefully that piece makes sense. If not, rewatch the videos.